All right, well, let's get started. Welcome everybody to today's webinar. My name is Alex Razumov. I'm from Simon Fraser University. And today we're going to talk about lossy data compression. So this webinar is supposed to be fairly informal. So if you have any questions, feel free to stop me at any time, ask questions via audio or in the chat. And I just pasted the link to the slides. So if you go to this website, it will open this page and there is a link to a copy of PDF slides. All right, so let's get started. So one of the biggest problems in modern day HPC world is that numerical simulations produce way too much data. And it's a challenge to both store these data sets, to write them in the first place because of bandwidth requirements. Because if you're producing, multiple hundreds of gigabytes or terabytes of data per, moderate size simulation, then it's very difficult to first of all store this and then to write this and then to store this long term, right? So if you decide to store, let's say, running a hydrodynamical simulation, and at each time step you produce, let's say, 10 or 20 variables, three-dimensional variables, and then you try to store all these variables, essentially your simulation is going to be dominated. I don't know, 98% of the time is going to be spent writing out data. So there are many solutions for this. One of the most common solution is just not to write all data out to disk, to write only partial data. For example, store every 100th time step, or store only selected variables, or perhaps even do in situ visualization. So in situ visualization refers to doing visualization right inside the simulation code, right? So where instead of writing your full three-dimensional or large data sets to disk, you're just writing much smaller visualization right during simulation. And then you can also do data compression. So data compression is great because you can effectively reduce the footprint of your simulations. So we all know lossless compression tools. So there is zip in Windows, in Unix world, there is gzip, bzip2, xz, and many others. So these compress data losslessly, and essentially what they do is they look for recurrent bits or bit patterns in your data, and then instead of storing all these recurrent bits, they just store them once, and then they also provide reference to every occurrence of that bit. And so these can, in general, these lossless compression utilities can compress your data roughly by 30, 40, 50%. So it's roughly by up to a factor of 2 in general. And often these lossless utilities included into the file formats. For example, the very well-known scientific file formats such as netcdf, HDF5, also VTK. File formats from the visualization toolkit, they all support built-in lossless compression. And so sometimes you can achieve actually higher than a factor of 2 compression ratio. So here's an example of a plot on the left where I have this three-dimensional fractal called Mandelbulb. So in spare time, you can actually Google Mandelbulb and see what it is. But essentially, it's a three-dimensional fractal surface that separates 2 volumes. So in the inside, you have one value of a variable, and on the outside, you have another value of a variable. And in this case, my data set, so the one you see in the picture, was computed on a Cartesian mesh at the resolution 800 cube. So if you do, 800 cube in single precision, if you just do the numbers, you will see that it should take roughly 1.9 gigabytes of data of space on disk. Whereas the actual netcdf file, if you open it, is only 12 megabytes in size, right? So here, this netcdf file has built-in lossless compression, so libz compression, and it's so effective in this particular case, it's compression by a factor of what it is, 170 or something like this, so by a huge factor, because in this particular data set, I have a lot of recurrent bits. So I have an integer variable that on the outside of the surface has one fixed value, on the inside of the surface, it has another fixed value. And even though, it has the surface has lots of intricate details, it compresses really, really well. But this is more often, exception, but more in general, when you're talking about lossless data compression, you're talking about, a factor of 1.5, factor of 2 at most on average compression ratio. And effectively, how well your data compresses with these tools is a litmus test for the efficiency of data storage, right? So if it compresses by, a factor of 100, a factor of 1,000, that means that you're just storing your data very, very inefficiently, and you probably should revise your IO strategies in the first place. But anyway, so this is lossless compression. And here we're going to discuss mostly lossy compression of three-dimensional data. So when you talk about lossy compression, you are really throwing away some bits in your data. And there are a number of ways you can do this. So first of all, you can, one of the obvious things, you can lower numerical resolution, right? So instead of, let's say, an 800 cube mesh, you can have a 100 cube mesh, and it's going to be, substantially smaller file size. You can lower precision. So instead of storing everything double precision, you can store in single precision. Or, there are libraries even for storing things in smaller precision. So instead of, let's say, 8 bits per number, you can do 4 bits per number, and so on. Then there are two large families, and this is what I'm going to talk about today. One is orthogonal transforms-based algorithms. So essentially, these are algorithms that do something like cosine transforms or Fourier transforms, and then throw away part of the transforms to save on storage. And then there's also topological compression. So these two methods are very different from each other, but actually complementary. So on the same data set, you can actually use both at the same time, and it gives you a very, very high compression ratio. And then finally, I also have, number 4 is compression by machine learning. So in principle, you can teach a machine learning, a deep network, neural network that, how to compress three-dimensional data sets, right? So you can, give it a lot of examples, and eventually it will figure out that, in compression, what you're doing is you're looking for prominent features, and you throw a lot of redundant things and so on. And nowadays, at this time, compression by machine learning is still not very well established. So maybe I will do a webinar on this, few years from now. But I think for the next few years, it's probably not a very reliable method to compress your data. And also in this webinar, I'm going to be focusing on compressing multidimensional arrays. So usually it's one-dimensional, two-dimensional, three-dimensional scalar fields, right? So not vector, but scalar fields. And what this means is, if you're running numerical simulation, let's say you have, I don't know, a galaxy formation simulation where you have density, temperature, pressure, velocity, fields like this, or you have a fluid dynamic simulation with similar variables, etc. So you have these three-dimensional distribution of scalar fields, and then there are certain techniques that can allow to compress these data very efficiently. So you can ask whether the same algorithms I'm going to show you today can be applied to other data. For example, in molecular dynamics, you essentially compute molecule atom trajectories. And can these be applied to atom trajectories? Well, the answer is yes, for sure, but you have to be careful because, MD trajectories is not exactly the same as a three-dimensional scalar field. So, the importance of bits and, relative weight of different bits is different when you compare these two data sets. But in general, yes, you can, but you have to be careful. So you have to know what you are doing. All right, so let's start with the first algorithm. ZFP stands for compression of floating point numbers, and it's a library that's been around for about 10 years now. So originally released, I think the original paper was published in 2014, so it's been around for about 10 years. And it's an open source project that was developed at Lawrence Livermore National Lab, supported by the US Department of Energy. And it's open source, so the source code is available on GitHub. It supports both lossless and lossy compression. Documentation is actually really good. So this website is actually an exception in that there are so many examples, and documentation here is really excellent. So the algorithm was written in C combination of C and C++, and the bindings for it are available in C, C++, Python, and Fortran. In Fortran, the library is called ZFPy, and you can install it using the usual methods, so pip, for example, pip install, or conda install, or whatever Python package manager you are using. So it's been built into 63 projects. So if you go to follow this link in the slides, you will see here the list various projects and software projects and various file storage formats, etc., that internally can use ZFP. And some of them are quite interesting. So I'm going to talk about a couple of them in the rest of the talk. So one of them is VTK-M. So VTK-M is a standalone implementation of VTK files for multi-core architectures. And internally, you can actually, from VTK-M, from multiple cores, you can actually store data with lossy compression on the fly. So the claim supported throughputs up to 2 gigabytes per second per CPU core, and you can also get a speed up acceleration on GPUs. It supports CUDA, OpenMP, FPGAs, and I have not tried it on GPUs. I just tried to do tests on benchmarking on regular CPUs. And in my experience, it's really, really fast. So it's actually very, very mature. So the algorithm, the details of the algorithm is listed on this website. I won't go into all the details, but essentially what it does, it relies on orthogonal transforms. So basically, you are doing transformation from a real three-dimensional space or two-dimensional space to essentially something that is similar to a Fourier space. So they're not using Fourier or cosine transforms. They're using something a little bit more efficient. But the idea is essentially the same. So you're doing transformation to this space where you only keep those transform coefficients that are important. So essentially, you reorder all transform coefficients, all components into a losslessly compressed bit stream, and then you truncate this bit stream at some point, and that gives you, depending on how you do truncation, that gives you a much smaller data set. And so you can do NZFP can do truncation in one of three ways. So you can do a fixed rate mode, where you specify a double precision number that essentially gives a fixed number of bits per floating number. And it's not an integer number, it's floating point number, because in some cases you can have, let's say, 2.5 bits per floating number, and that will give you the best combination of file sizes and quality of output files. Then there is the fixed precision mode, where there is an integer parameter specifying the number of bit planes. So essentially, it's a number of coefficients that you want to keep, and it's an integer number. And then the third mode is you can have a fixed accuracy mode, where for each variable that you're compressing, you're specifying the maximum point-wise variable error. So I'm going to show you an example in a few minutes. For example, you can say that I'm going to have this three-dimensional array compressed down to the area of 10 to minus 3, and NZFP will do that for you. So let's do an example. Let me open. So I'm going to be showing lots of different windows. So I'll be copying a code from my text editor on another screen, but essentially all code is right here on the in my slides. And once again, I'm going to paste for those of you who join in late, I'm going to paste the link to the slides. So here's a very simple example where I use the FP from Python, and I initialize a tiny array. So as you can see, the array has only 10 numbers, but I store these numbers not as integers, numbers from 1 to 10 inclusive, but as single precision, so float 32 floats. And let me just start Python right here. So I'm not sure how to best position it when I have multiple windows. Let me move it slightly up. So I'm going to start Python, and then I'm going to import NumPy and the ZFP library, library. And then I'm going to initialize the array. So my array is going to be a set of floats from 1 to 10, float 32 variables. And then first, I'm going to show you how you can do lossless compression with ZFP. So all you do is just say compress NumPy array. So remember that with ZFP, you compress not files, but you compress arrays. So in this case, we have a one-dimensional array that we pass to compress NumPy function. And then if we look at the result, you see that it's essentially a bit stream, right? So it's a collection of bits that you can save to the disk. So in this case, we are dealing with lossless compression. So there is no loss of bits. And then if we uncompress it, so the function is decompress NumPy, so opposite to compress NumPy, and then we print out the result. You see that the result is exactly the same as the original, simply because we did lossless compression. So it is lossless compression because I did not pass any arguments, any additional arguments when I was doing compression. So I did not specify the number of bits, the number of coefficients, or the tolerance. So as soon as you start specifying one of those arguments, you will get lossy compression, where you throw bits past some threshold. So let's try this. Let's try lossy compression, where I'm going to set up number of bits to 4. So that means that I'm storing numbers at 4 bits per floating number, right? So that's essentially not single precision, but half of single precision. And so let me initialize the array and then compress it. So the array is exactly the same array, and then it compressed to this bit form. And then when I uncompress it, so I pass the compressed back into the decompression utility, and then I print the decompressed array. You see that now it is different, right? Because we are now dealing with finite storage, so we specify 4 bits per floating number. At that precision, for this particular example, the efficiency is not really great. So as you can see, we get the answer, which is quite different from the original, right? And in fact, so I did a study on this particular case. So here's in this particular case, when you try to compress these numbers from 1 to 10, here's what you get. So depending on so here's my array, the element index on the horizontal axis, and on the vertical axis, I have the floating, the compressed and then decompressed value. So this is what I get, after compressing and decompressing. And as you can see, depending on the rate, so as I increase the rate, as I move from blue to red, my compression quality increases. And actually, I get the exact result starting from the bit rate of 6.63, roughly 6.63 bits per floating number. I get the exact result. So in order to write this into a file, what you do is you simply you simply have this compressed variable, and then you write it as a binary stream, right? So just in Python, just open a file for writing in binary mode. I gave it a ZFP extension. There's no unique convention of what extension you should give it in this case. So I just give it a ZFP extension so that it's clear that it's a ZFP compressed file. And so let me compress it. So here I simply paste the last 3 lines, and then I get the file, which is 24 bytes long. So let me just verify this. So the file is compressed ZFP, and it's 24 bytes long. So some of you might notice that here's a mismatch, right, between the number of bits and the actual file size. So my bit rate is 4, so I'm using 4 bits per floating number, and I have 10 numbers. So that number of bits that my storage should take, number of bits, this is the number of bytes, right? So my storage should take exactly 5 bytes, and it's actually 24 bytes. So the reason for this is because it's not only these numbers that are stored here, but it's also the arrays, the length and the shape and the type of the array that is stored here. So it's extra 19 bytes that are devoted to that. But as you go to as you start going to bigger and bigger arrays, then the efficiency of your storage is going to be much better. So here's the next example. Here is a function that is basically a mathematical function. So you will see, I will visualize it in a few minutes. It's a mathematical function that I use for teaching visualization quite a lot. And basically, you don't have to worry about the specific function itself. But here, the function is, it has lots of interesting features, local maxima, local minima in 3D space, and basically is defined inside a unit cube where x1, x2, and x3 go from 0 to 1. So I computed this function on a 300 mesh, and then let's just do the calculation. So if I do 300, if I have 300 mesh, and this is the number of mesh points, and then if I store it in double precision, so 8 bytes per number, this is the number of bytes that is going to take on disk, right? So if I convert it to megabytes, it's going to be 206 megabytes, right? So when I save this file, it's 206 megabytes. And then if you want to try to do lossless compression with this, so the standard GZ tool, GZ or gzip tool will give you compression almost by a factor of 2, right? So from 206 megabytes, you can go down to 125 megabytes. The best you can do with command line compression tools is bzip algorithm, so bzip2 algorithm, and that lets you compress a little bit better than the gzip algorithm. But in both cases, as you can see, so this general function can be compressed almost by a factor of 50, by a factor of 2, 50%. So not factor of 50, but factor of 2, 50%. But you cannot really go much better than this with this compression. So you can also save it as a netcdf file, and I mentioned before that netcdf has built-in compression, right? So if you compress it with a default zlib algorithm inside netcdf, then the file size is going to be slightly better than the original, so it's going to be 159 megabytes. And then with the very aggressive zlib compression, where you keep only 3 significant digits per number, so now we have, this is already lossy compression, right? You can go down to 33 megabytes. But the point here I'm trying to make is that, you cannot really, with lossless compression, you cannot really do much better than a factor of 2 compression. So let's apply ZFP to it. So here in the next code, I'm going to read this netcdf file, which is 206 megabytes, right? So just to verify, ls minus l double 300 and c I'm reading is 206 megabytes. And then I'm going to compress it. I'm going to compress it at the rate of 2 bits per number. And then I'm going to save it. So let's do this. Let me jump into Python. And let me find the example. So here I import the libraries and I read the netcdf file, and then I compress the netcdf file. And now the length of the compressed array right here, this is the length in bytes. So if we convert it to megabytes, it's going to be 6.4 megabytes. And this is actually now consistent with this number of 2 bits. So I'm using 2 bits per floating number. So if you do, there are 300 cube numbers, right? Oops, cube numbers times 2 bits. So that's number of bits divided by 8. That's number of bytes, and then convert to megabytes. The file should take exactly what I just mentioned, 6.4 megabytes on the disk, right? So let's just save that compressed array. We're going to save compressed array as a file, and now it should be 6.4 megabytes. How do you read it? Well, to read it back, you simply read the binary stream from the file, so read binary from this file, and then you put it into this compressed array, and then you decompress using the same decompress numpy utility. And then optionally, you can actually convert it back into the netcdf file. And the reason I converted here, right here, back into the netcdf file, simply because I cannot, so I'm going to visualize this array next, and I cannot read the ZFP file natively inside ParaView. So in this case, I uncompress it, and then I convert it into uncompressed netcdf file, and then I will import it into ParaView. So first of all, let me show you what it looks like in original. So I'm loading ParaView. And by the way, notice that here we have compression by what factor? So we have 206 divided by 6.4. So we have compression by a factor of 30, which is not too bad. So compression by a factor of 30. So let me load the original file. So the original file is going to be double300.nc, and then using the netcdf reader. And this is, let me do one of these, do a clip, and then show you the function. And this is what the function looks like. So with ZFP compression, I find that a better way to visualize it, so this is the original function. A better way to visualize this function is, instead of doing clips, is actually to do an isosurface somewhere at the medium value of the variable. And once you start getting noise, you will start seeing noise from compression artifacts on this surface. So let's do the second one. Sorry, let's go to, let me do, so here what I did, let me actually, so I wrote compressed ZFP file, and then what I'm going to do next is I'm going to read this file in Python, and then I'm going to convert it to back to a regular netcdf file, but only keeping the compressed bits, right? So let me decompress it. So let's see, do I have the compressed data? No, I don't have. So let me read the compressed file. So here I'm reading the compressed file. Oops, sorry, reading, not writing, reading the compressed file right here. And then I'm converting it to a netcdf file. So f close. And now I have a file, compressed.nc, that has this compressed data set, decompressed now data set, that is stored as a netcdf file. So let me go back to ParaView, and let me actually hide these guys, and now load the compressed file. So it was, I forgot what it is, compressed.nc. So now this file is 6 megabytes large, so it's 30 times smaller than the original file. So if I look at the cross-section, you will see that visually it is essentially the same as the original file. As I mentioned, it's probably best to look at the isocontours of a variable somewhere at the median value. And here's an isocontour. So if you compare this to the original isocontour, you see that there is essentially no difference. Visually, they look exactly the same. And this just shows you, how efficiently you can compress you can use ZFP for compressing three-dimensional arrays. So here I have a compression by a factor of 30, and I cannot find any difference when I inspect the compressed and decompressed array. And in fact, you can actually, on your own, you can try to play with high compression ratios. So you will start seeing some compression effects at the rate of 1 bit per number, and that's already a factor of 60 or so compression. So there are other, some notable storage formats supporting ZFP. So those of you who work with HDF5 files, please know that HDF5 has support for ZFP. So there is a package H5Z-ZFP, that lets you do this compression on the fly. I already mentioned VTK-M. In Julia, you can use ZFP directly. So there's a package in Julia called ZFP compression.gl, which is a wrapper around the C library. So internally it uses C, but on your screen, you actually uses all the familiar Julia syntax. And actually, let me show you next the demo of Julia, and then I will jump to a ParaView demo. So you can actually do this compression with ParaView as well. So in Julia, I'm going to use this library, ZFP compression.gl, which is wrapper around the C ZFP library. And again, if you use it, if you call the function a compression function, so ZFP compress without any arguments, then you get lossless compression. So as soon as you're starting to specify one of these numbers, so either tolerance or precision or the bit rate, and precision is integer number of coefficients that you're leaving, that you're keeping. So now you're doing lossy compression here. So let me jump quickly into Julia. And in Julia, so here, I'm going to load the ZFP compression library, and then I'm going to initialize an array. So this is an array of flow32 at 100 squared resolution. So it's a two-dimensional array, right? Just floating numbers, uniformly spread between 0 and 1. And so with lossless compression, all I need to do is just say ZFP compress on this initial array. And here's my compression. Let's see if copying from PDF works. Yeah, so here's my compressed array, basically a collection of bits. And then I can inquire about the size of this guy. So the initial array was 40,000 bytes. It was 100 by 100 single precision. And then the compressed array is 34,000 bytes, right? So this is not a huge compression ratio, but here I'm dealing with lossy compression. And also notice that my array is a random array. So in general, it's much more difficult to compress random data as opposed to, structured or, more uniform data sets. So let's try lossy compression. So with lossy compression, I'm going to specify tolerance. I'm going to say compressed to this tolerance of 10 to the minus 3, right? So now my array is compressed. This is the original array. This is the compressed array. And now I can decompress it. So now my result is in decompressed array, which I can print if I want, right? So it looks good. But what I can do is I can compute the maximum error between the initial and the decompressed array. And as you can see, because I specify the error of tolerance of 10 to the minus 3, my maximum error is actually under 10 to the minus 3. So exactly what I specify, right? So this is really good because you can actually, for any variable, any multidimensional variable, can simply specify tolerance, and ZFP is going to compress to the tolerance. So the maximum error on anywhere on your grid is not going to exceed that number. And so in terms of compression size, let's check how large this array is. So my original array was 40 kilobytes, and the compressed array is 17 kilobytes, which is a factor of 3 or so compression. So I mean 2.5. This is not great, but again, notice that you are dealing with first of all random arrays, which are harder to compress, and also you are keeping more bits now, because now you're asking to leave essentially 3 significant digits for every floating number. And then you want to save it to disk, you just write, just use this command. So write command and then read command to actually read it back. And you can follow these examples and everything works nicely. So in ParaView, which is one of the most popular visualization utilities, you can also have ZFP compression. And the way this is done is by the TTK plugin. So TTK stands for Topological Toolkit, and it's another tool that I'm going to talk about. And I'm going to talk about this in the next section in a few minutes. But the nice thing about TTK is that not only it's already included into precompiled ParaView, but it also lets you. So there are options that let you use TTK's compression without actually doing topological compression. So you can just hit a checkbox enabling only ZFP compression. So let me show how to do this. So first, let's start in ParaView from scratch. So let me unload all the data. And one thing, the first thing you want to do is you want to make sure that you enable the, so in Tools, Manage Plugins, make sure that you enable the TTK plugin. So right here, Topology Toolkit plugin is loaded. And you can also do this via XML files. So for example, I like having, I have this script enable TTK, and essentially what it does is a function that flips a bit, so from 0 to 1 in this XML file, which is inside my ParaView installation. So every time I start ParaView, this way the TTK plugin is auto-loaded. So anyway, let me load the data set. Let me load this original NetCDF data set. So NetCDF reader, as you can see, it's double precision, and it is 300 cube mesh. And then in order to save it with a ZFP only compression, what I'm going to do is I'm going to go to File, Save Data, and then for the image file type, I'm going to save TTK, and then check the box ZFP compression only. So let me do this. So my data is loaded already. I'm just not visualizing it right now, but I'm going to go to File, Save Data. And then for the file type, I'm going to use a topology toolkit. And I'm going to use, let's say, this file, 111.ttk as an example. Yes, want to override it. And so here is the box, use ZFP compressor only, not topological compression. I'm going to enable it. So now I'm using ZFP only. And here's a slider that gives me the relative ZFP errors. So if I enable very large error, the default one is 50% error. So that means 50% at each point relative to the actual number. And then I'm going to say, OK. So now it saved it. ZFP is very fast. And now my file is 1.6 megabytes. So if you do the math, 206 divided by 1.6 megabytes, now you see that you get a factor of 128 compression. So let's see what it looks like, the compressed file. So now I'm going to open the file that I just saved, 111.ttk, with ZFP compression only. So here's my file. And now if I build the isosurfaces, you will likely see an error. So here you can see the error, right? So here now you see that this isosurface this isosurface is kind of noisy. And this is just the artifact of compression. So, when you go to compression ratio of 100 or higher, you actually start seeing artifacts. But the function still looks fine, even with that extreme compression ratio, for many visualization purposes, let's say I want to do a clip and visualize my variable, it still looks just fine, right? So here, it's a little bit noisy if you zoom in it, but it still looks fine. And this is more than a factor of 100 compression. All right. So you can also do this via ParaView Python. So in ParaView, you can script this whole dialog that I just showed you in the GUI. And the way you do this, so here's my code. And this code, you can actually start PVPython, which is a utility for running ParaView flavored Python scripts, right? So here, I'm just going to paste the script. So in the script, let me find it in my notes. So here's the script. And what I'm doing here is I'm reading the data, the netcdf file, and then I'm compressing it at 50% error into the file 300.ttk. And because I'm using 50% error, it should be 1.6 megabytes. So let me verify that. And it is 1.6 megabytes, right? So here is a table that just shows, the compression ratio, the file sizes, and the input parameter, and the quality, perceived quality as well when you visualize it, let's say in ParaView. And as you can see, so when you start with 206 megabyte file, and then I compress it down to, let's say, 1.6 megabytes, so that's the 50% ZFP relative error, I get a compression ratio of 129, and my data is noisy. So if I use 20% relative error, my data set is still quite noisy, but then noise goes down as I go to larger and larger file sizes. And so here I, just by visually expanding this, I find that the data set looks essentially the same as the original at 5% relative compression ratio. So that gives me a file size of 3.1 megabytes and a compression ratio of 60. And at this point, I actually don't see any error. So unfortunately, I have lots and lots of content in the slides, and I have to speed things up a little bit because otherwise I won't be able to show you everything. But here's the last slide on the ZFP compression. So here I have a data set which is a numerical simulation of deep water asteroid impact. And this data set comes from an IEEE visualization contest from 2018. And the reason I'm using this data set is because it's very cool. So it gives you, a real numerical simulation that you can try to compress with ZFP. So let me show you first what this data set looks like in originally. So original file is, let me just open this. I will go into deep water impact. And so the original data set contains multiple variables. So it actually, in the competition, was provided as a VTK file with a bunch of variables. All of them are single precision variables, but they are compressed with lossless compression. So the resulting file was 1.3 gigabytes. Because now I want to focus on a single variable. I extracted from this data set, I extracted a single variable called sound speed. The reason I took sound speed is because it just visualizes very nicely. And so I store this as a double precision variable. So my data set is 500 cube, double precision. That means that my file is 954 megabytes large, so almost 1 gigabyte. So here's my file. Let me go into this directory. So the file is called smd.vti. It's 954 megabytes. And let me load this file first, and let me show you what it looks like, smd.vti. So as you can see, it's a 500 cube data set in double precision, just a single variable called sound. And then if I visualize it, let me do a cross-section in this direction. So this is essentially a variable, but here I'm doing cross-section, but it's discretized on a 500 cube Cartesian mesh. So here you have a three-dimensional distribution, and this is actually what the original data set looks like uncompressed. So let's compress it with ZFP. So here I run the script that compresses it. And I do it in, so again, I can do it in a number of different ways. I can do it in Python. I can do it in Paraview GUI. I can do it in Paraview Python. So here I'm running just this very simple script in Paraview Python. And in fact, let me do this. So I'm going to say PV Python. And then I'm going to run this script. So here in the script, a very important thing is that you enable ZFP compression only, right? So this variable, this argument is set to 1. This gives only ZFP compression, no topological compression. And then now it is doing compression, so it should not take a very long time. And then, so depending on the value of the relative error tolerance, you will get different file sizes and different quality. So the example I showed you was run at, let me see what it was. It was run at 50% error, and I saved it into a file zfp50.ttk, but this is only ZFP compression, so zfp50.ttk. So I went down from 1 gigabyte, from 950 megabytes down to 2 megabytes. So that's a compression ratio of almost 500, right? Almost 500. So let's see what this looks like when I load this file into Paraview. So let me unload this data. And then let me navigate to the file, zfp50.ttk. And then I'm going to say apply. So here's the data is read. Then let me do the slice and collate by the variable. And so here is what I get after compression. And if you compare the original plot to this plot, you will see there are some small errors. But remember that here we're talking about the compression ratio of 500, which is really, really amazing, right? And in fact, with this particular data set, I find that starting from the compression ratio of 200, I stop seeing any differences between the original file and the compressed file, which is quite amazing. So you have a factor of 200 improvement in file storage efficiency. So let me jump next to the next topic because we have only 20 minutes left, and the next topic is actually even cooler. There's more material. So I unfortunately won't be able to show you all the slides, but the slides are available online, so you can study them after the fact. So the idea is to use topology-based analysis for compression. So what we're doing is we're looking at a scalar field in the data, and then we are looking at various measures or various attributes of topological connectedness. So there are many things you can pick up here. You can study, for example, you can pick up any 2 points on, let's say, a 2-dimensional plane, and then find an inside path to connect these points. So, and then you can quantify that. You can count the number of non-contractible cycles. You can count critical points, et cetera, et cetera. So here's an example of the variable that is used directly for topological compression. So let's say we have this function, one-dimensional function, that we try to compress topologically. And what we'll be looking at as we sweep this function from -infinity to infinity. So we'll be going, actually, draw here. So we'll go from -infinity to infinity in this direction, right? We're going to count the number of components. So as I go, reach this critical point and go slightly up, I have 1 component. Then I keep going up, I have 2 components. Then I have 3 components. Then I have 2 components. right? So now my third component only lived for a short time, right? So my third component was born here, and then it disappeared here, right? So now I'm back to two components. Now I'm back to one component. So component number two had a lifespan between these two critical points, right? So this is the second component, and then this is the third component, right? So in this particular example, I have three topological components. And then you calculate their persistence value. So essentially the length between their birth and their death, right? So the lifetime of these values is called their persistence intervals. And you can map these onto these graphs, so XY graph, where the X, the horizontal coordinate, is the time of, well, the value of the function corresponding to the birth point of these components. And then on the vertical point, I have the death point of these components, right? So essentially the vertical extent of each component is their persistence value, right? So here I analyze the function and I find that I have a certain number of, critical points and a certain number of components. I quantify these components on the persistence diagram. So you can visualize this very easily in 1D. So in 1D, the critical points, these critical points are just maxima and local maxima and local minima, right? In 2D, things are a little bit complex. So as I sweep my function from the function value minus infinity to plus infinity, I have different components, and then I quantify them. And so essentially here you have three types of critical points in addition to local minima and maxima. You also have saddle points, which are, in one direction it's a minimum, in the other direction it's a maximum. And then in 3D you have, two types of saddles. So you have four types of critical points. Now we're talking about a three-dimensional scalar function, and then four types of critical points. So all of this was coded into this wonderful package called the Topology Toolkit, which was, so again, it's open source. So first release also in 2014, so it's been around for about 10 years. And a few years ago, it was incorporated so it was coded in C++ and VTK. And a few years ago, it was incorporated into ParaView. So now when you download ParaView, TTK is also enabled. So the way you use compression in TTK is you can do it in one of three ways. You can do it in pure Python. You can do it in VTK in Python, right? So these will give you a shorter code, or you can do it inside ParaView, either in GUI or in ParaView's PV-Python. So, and how topological compression works. So here, the algorithm is actually very, very different from the previous algorithm. So in topological compression, what you do is first you do topological simplification. So you remove all features below a user persistent threshold, so epsilon. So basically this tolerance is the first number, and then any feature that has the persistence value smaller than this number, you remove via topological simplification. Then you do domain quantization. So you break the domain into regions, and then you try to encode the remaining data using some topological descriptions. So I'm going to show you a few pictures that visualize this. So going back to our function, what is topological simplification? So this one-dimensional function has these three components, right? So 1, 2, and 3. And then let's say we decided that we're going to throw things, things smaller than this tolerance threshold. So that means that we're going to throw away the smallest component, this guy. So our function simplifies. What we do is we basically remove the critical points that correspond to these smallest components. So here we have just a constant value of the function. So here's a topologically simplified one-dimensional function. And then here's an example of two-dimensional simplification. So I'm actually going to show you an example on. So if I go to Lossy and then open as these files, so here I construct in ParaView a two-dimensional function with a bunch of Gaussians, and then as I simplify it, you see what happens. So basically, I remove progressively larger and larger peaks, right? So I replace them with constant values, and these peaks then it can be both pluses and minuses, but all of them are essentially replaced by fixed planes, right? So, and then after topological simplification, after a threshold, you are left with remaining components. And these remaining components, you try to describe topologically. So in this example, after removing this smallest, let me maximize it. After removing these smallest components, now we have a flat a plane here, a fixed value. So now we have with three intervals. So here in this interval, we have just one component. In this interval, we have two components. In this interval, we're back to a single component. So now we try to represent these regions with the respective number of intervals via fixed planes. So here, let's say, here's my first region, right here. So here, the function is represented by a constant value, and there's also a critical point. So in this region, the second region, the function is represented by two components. So these are, I'm trying to approximate these components by constant values. So these are the components, this is their value. And I have these critical points right here, right, at the border of this region. And then in region number 3, I have again a single component, which is represented by this value, right? And then what I do is I go through all points on my mesh, because I remember my data is originally discretized, in this case, on a one-dimensional mesh. And then at each point, I estimate essentially the error with which I'm encoding this data, right? So here, for example, at this point, the error is fairly large, right? And so on. So you basically, in every region, you compute the maximum error of these, with this approximation with constant planes. And then if the error is larger than a threshold, so here's very important, here's this user-specified error. So there are two numbers now that are important in topological compression. The error is bigger than threshold, then you refine that region. So basically, instead of having just a single plane, single value for these planes, you have two values for these planes, right? And then you iteratively keep iteratively refining those regions where the error is bigger than the threshold. So here's a couple of plots from the original papers on topological compression. So I'm going to skip this one because I already showed this. But here's what you have in 2D. So in 2D, instead of having these constant regions, you have these constant regions, which you try to store using as few bits as possible, right? And then you iterate. When you need high precision, you simply double the number of these planes in that region, and then you do it iteratively until you represent your function, your discretized function well enough. So how does it work in the GUI? Well, in the GUI, very easy. You simply go, again, you load the file, and then you try to save it, go to File, Save in Preview, and then you try to enable TTK compression, right? And then you specify these two numbers, topological persistent tolerance and maximum point-wise error. So let me go to these guys, to Preview. So let me start from scratch. I'm gonna load the gonna go back to Lossy, gonna go load the original double 300 netcdf file. So it's a 300 cube data set, double precision variable. And then I'm going to go to File. So click on the data in pipeline and then go to File, Save Data. I'm going to save it as, let's see, 222.vtk, topology toolkit. Very important that you choose TTK file format. Yes, going to override 222. And then here, I'm going to use these two sliders. I'm going to use topological loss. Let's say the default value is 10%. And then can also modify the maximum point-wise error, so also 10%, right? So these two numbers, this number and this number, these two numbers control topological compression. And then optionally, you can also specify ZFP error. So I'm going to specify set it something very small, like 1%, so that our compression is mostly given by the topological compression. So I'm going to say OK. And so now it is compressing, and topological compression is slower, much slower than CFP compression, because there's quite a lot of analysis there. But this will take about 30 to 40, maybe 50 seconds, and then it'll produce the file 222.vtk. So if you look at the size, so it's still computing, if you look at the size of these files, let's see, do I have it for? Yeah, right here. So if you look at these files, so here, let me actually increase, let me increase the zoom in on this picture so I can actually see better what is going on. So now with topological compression, there are two important parameters. One parameter is tolerance. So in TTK implementation inside Purview, both parameters are in percent relative to to the maximum value, to 100%. So tolerance of 50% means that basically I am removing all components that are smaller than 50% of the largest component, right? So here in my cross-section, as you can see in this sine wave function, I had lots and lots of components, and I remove all components smaller than topological components smaller than 50%, 50% of the maximum persistence value. This is what I get, right? So I remove a lot of components, and then after I remove these components, I try to approximate the remaining components, what you see on the screen, with these stepwise functions. So I can actually see, you know, when you visualize it, you can get kind of a stepwise function, right? So 10% error for the stepwise function, you see that you get quite a lot of artifacts from compression. So now if I reduce the error to 1%, let's see if I can do, yeah, if I reduce the error to 1%, so here's a plot at 50% tolerance and then 1% error, you can see that I'm throwing here, so in both cases, I'm throwing away the same components, but I just, how well I encode the remote components is given by this second error argument, right? And so as you can see, if you vary the number of components, vary the tolerance for the components that you throw away, you see that as you reduce the tolerance, essentially at some point you keep all the components. So if you have the tolerance of 30%, you essentially more or less keep all the components. And then if you encode it at 1% error, so tolerance 30%, error 1%, you see that my file size is 11 megabytes. So I went in file sizes from, so in this case, 206 megabytes down to compression ratio of 20 or so, and then I get a result which is looks identical to the original result. But it's very important to remember that with topological compression there are two parameters. So one parameter is basically let's specify threshold below which you throw all the components, and then the second parameter is how well do you encode the remaining components, right? So if I go back to my example. So this is how I would do this in ParaView Python, right? So and in the background, this was actually running and it's saved into the file, I guess, let's see, ls-t into the file, these guys. So this took maybe 30, 40 seconds. So the file is 6.9 megabytes, so much smaller than the original file. So you can also do this in ParaView Python. So in ParaView Python, you simply run this code, right? So start PV Python, and then this is essentially the same workflow as I did in the GUI, except that now you do this via ParaView's flavor of Python. So you specify the maximum tolerance, which is right here, right? So 10% is default value, but you can specify any number you want. And in our particular case, we saw that 30% is actually pretty good. And then you specify the maximum error, right? And so this is for ZFP compression. If you don't want ZFP compression, you can actually set it to -1, and then it will not compress using ZFP. So, and then finally, you can actually use it from C++. So this is, in my opinion, the easiest way to use it. But to do this, you have to install TTK. And in my particular case, because I'm showing you all demos on my laptop, I try to install it from the TTK website. They actually have precompiled binaries. But it turns out the precompiled binary doesn't work because it was compiled for Intel macOS. And while Intel macOS applications work on Apple Silicon laptops, a command line binary will not. So you actually have to compile it yourself, but it's fairly easy to do. So here's how I compile essentially. Just run cmake and make. And then once the TTK library is compiled, here I have the code. It's a C++ code, which essentially reads the original data. So here I specify a bunch of parameters in the C++ code. And by the way, it took me 3 full days to actually run and debug this code before everything works. So this is an important code in the sense that all these finite details you cannot find in documentation. So unfortunately, this is documented very, very poorly. But anyway, so here what I'm doing is this code takes in up to 4 parameters. So 2 of them are mandatory: the path to the input VTI or VTK file, path to the output TTK file, and then 2 parameters are optional. So the tolerance and the error. If you don't specify these guys, they're going to be 10 and 10% respectively. So here I'm reading the input VTK file, and then here I'm setting here the parameters for compression. So default values are 10 and 10% respectively. I can also specify no ZFP compression by setting ZFP tolerance to -1. And then here I'm writing the file, right? So I'm writing the file, and the output result is going to be exactly the same as, for example, in ParaView GUI, but here I'm just doing everything via command line. And then the way you run it is, well, you just use a command similar to this one. So let me show you the demo. So here I'm inside the Lossy directory. I already compiled the code. So if, just to show you how it compiles, you have to link to quite a lot of TTK libraries, but here's how we do it. And then to run the code, I simply run the code. I'm going to say input double 300.vti file, and then use, let's say, let's do, I don't know, 1% tolerance, and then the error of let's actually do 10%, let's do 20%, and then the area of, let's say, 5%. So that should compress pretty well and still give a pretty good quality. And then the output file I'm going to save to 300.ttk. So this will, oops, something I did wrong. So minus input file, minus I. So, and as you can see, it gave this TK logo, and this will take about 30 seconds or so to compress, and then it will output the file. So if I look at the very last example on the deep water asteroid impact collision, so here my file is 954 megabytes, and then I compress it with various combination of parameters for the tolerance and for the area. And you can see that, so I can achieve fairly high compression ratios, but at some point I will start getting errors. So here I go from larger files to smaller files. And as you can see, so here I actually, sorry, here these are larger files. So what I'm doing here is I use default 10 and 10% respectively. And then I try to improve on one of these numbers, either have smaller tolerance or smaller error. And then I see that essentially the result looks identical to the previous result. So in these cases, the result looks exactly the same as here. So that means that this combination of parameters right here is already fairly accurate. And so here I get a compression ratio by a factor of 99, so a factor of 100, right? Went down from 954 megabytes down to 9.6 megabytes. And by the way, I'm still using double precision. So I'm still using the original grid resolution, 500 cube, still storing data in double precision. It's just I'm also enabling on-the-fly topological compression, and I get virtually undistinguishable results at 100 squared compression. So let me just quickly show. So if I, so here already compressed, right? And then let me load this file, TTK file into ParaView. So TTK files can be loaded directly into ParaView. So here I have deep water asteroid impact, and then the file. Oh, actually, sorry. Actually, let me load. Let me go to deep water asteroid impact. I want to show you because I'm almost out of time. I want to show you this result. So let's see the one that was compressed with a factor of 100. So T10E10.ttk. I'm going to load that file. So T10E10 file. So compression ratio of 100. And so now it's going to take maybe 30 seconds to actually load it because now it's uncompressing. So doing, topological decompression, and it's take a while, so the algorithm is fairly slow. But when I visualize it, you will see that it's essentially undistinguishable from the original file. So while it's doing this, let me show you the last slide, and then I'll go back to the ParaView window. So the last slide is I presented two methods, ZFP compression. So ZZ stands for zipping floating point arrays, and topological compression. They're quite comparable in output file quality and file sizes. Both of them I find with generic data, generic three-dimensional data, non-random, but more ordered data. You can very reliably achieve 20 to 30 factor of compression, so reducing the file size by a factor of 20 to 30, without any visible data degradation. I tried many different data sets, and sometimes as high as a factor of 100, or maybe factor even of 200. And then compression artifacts show in different ways, in very different ways in this algorithm. So with ZFP, you get essentially noisy compression because you're showing, you're throwing away high oscillation, typically high oscillation bits. And these show as noise when you do your isosurfaces, for example. With topological compression shows in different ways. So you throw away smaller components. So you're left with few components, and then the remaining components you're representing with piecewise constant functions, right? So instead of noise, you have piecewise constant functions and a few components. So you can combine both methods for improved quality, and there's actually a page in this. So in the TTK documentation, there's a page that shows exactly what will happen. So I'm not going to talk about this now. You can do it on your own. But because these two methods act on different bits, you can actually get further improvement by using both of them. So topological compression is much slower than ZFP, but it has some pluses. So one of them is it provides more control. So instead of one parameter, it has two parameters. It also preserves variable bounds. So this is very important. So with ZFP compression, you can have a non-physical value on the output. So for example, pressures or sound speed, that also always physically positive variables. After ZFP compression, then you can have negative values of these variables. With topological compression, you cannot do that because topological compression always preserves the the largest components, so the global maximum and the global minimum, they're always preserved. So that's why the variable bounds are always the same as after compression as before compression with topological compression. So also remember that both algorithms work not on the files, but on scalar arrays, right? So you cannot just take a random file and pass it to it. It actually has, these algorithms, they look at spatial distribution of variables, and they actually compress it in certain ways. But you're talking about array compression or spatial variable distribution compression. So ZFP is available by C, C++, Fortran, Python. There's also Julia binding. Topological compression, currently, the only widely accessible implementation is available via TTK, but the way you can run it is you can do it via Paraview, GUI, or scripting. You can do it via C++ and VTK. And in principle, also, so far I just showed you compression of data sets of uniformly spaced data sets, defined on top of Cartesian meshes. But in principle, with topological compression, you can also compress multi-resolution or AMR, adaptive mesh refined data sets in one go. In one go, I mean, as opposed to, if you have lots and lots of meshes, let's say in block structured AMR, you can compress with both ZFP and topological compression individual subgrids. But with topological compression, you should be able to compress everything in one go, because in topological compression, there's actually no built-in spatial information, essentially, right? It's the number of components, in this topological analysis that is variable. But where these components are sitting, topological compression doesn't really care. They could be defined on a single grid. They could be defined on a multi-resolution grid, or on a number of uniform grids. And so, in principle, in that sense, topological compression can be applied to AMR or multi-resolution data, although I have not seen any implementations of these, but I'm fairly confident that it can be applied to multi-resolution data as well. So finally, let me go back to Paraview, and let's just, so here it loaded. I loaded the TTK file, and let's see where it is. So here's the file. Let's draw a cross section. So here is my data after a factor of 100 compression via topological compression. So now it's doing the cross section. Actually, I did a clip instead of cross section. Doesn't matter. So, and then I will go to color by the sound. As you can see, it's almost undistinguishable from the original distribution. So now we're talking about a three-dimensional variable that was compressed very, very efficiently by a factor of 100. And you don't really almost see no artifacts when you compare the original visualization and this output, this resulting visualization. All right, so I'm going to stop now. We're out of time, unfortunately. But if you have any questions, please let me know. I'll be more than happy to stay around and answer any questions.